In this lecture, we're going to perform a multipole expansion on the magnetic potential. So we did something similar with the electric potential. So we expanded it, and what we found is we expanded it into terms of a single charge, a dipole, a quadrupole, an octopole, and so we want to try and do the same thing for magnetic potentials. So if we look at the magnetic potential function, we have A is equal to mu 0 I over 4 pi, the integral of a closed loop, 1 over r, integrating over dl prime. Now in this case, I'm taking a specific case where the current or current density, depending on if it's a line current or surface current or volume current, is uniform. So I can pull it outside of the integral, and I'm left with basically the integral of 1 over r integrating over dl. So first, let's draw a picture of what I mean by script r. So let's say this is our current flowing in this direction, and we're going to pick a point on the current and measure from there, and that's going to be the distance r prime. And then we're going to pick a point in space up here, a distance r away, and that's where we measure the magnetic potential. And so the difference between these two vectors is the script r. So now the angle between these, I'm going to call alpha. So that means I can now write out this 1 over r in terms of the law of cosines. Like so. And then what I can do is I can perform a perform an expansion of this to change the 1 over square root function into a sum of terms. So that now becomes 1 over r, the sum, n equals 0 to infinity, of r prime over r to the n power times the Legendre polynomials. And I should be careful, that's not theta, that's alpha. So, okay. So then what we can do is we can take that 1 over script r and plug it into our formula right up here. And then integrate. Okay, so let's do that. So let me write down our function. A is mu 0 I over 4 pi, the sum, n 0 to infinity, 1 over r n plus 1, because there was an n inside the summation, and there's 1 over r in front of the summation. And then we integrate over everything that is primed. And so we would integrate over r prime to the n power, the Legendre polynomial, cosine alpha, and then we integrate dl prime right there. Okay. So now basically at this point we just need to integrate term by term, so we can write out a few of the terms. And what we get is mu 0 I over 4 pi times 1 over r. So this is the n equals 0 term. 1 over r, the integral dl prime, because the first Legendre polynomial when n is equal to 0 is just 1. And if n is 0, then r prime to the n is r prime to the 0 is just 1. So we just get this term. and then we get plus 1 over r squared, integrating over, now this is the n equals 1 term, so r prime cosine alpha dl prime plus 1 over r cubed, integrating over r prime squared, and then the Legendre polynomial is 3/2 cosine squared alpha minus 1/2 dl prime dot 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 higher order terms. So this is the first 3 terms. Now if you remember that the divergence of the magnetic field is 0, so there are no monopoles. So I don't have the case of a single charge. There is no single magnetic charge. It always has to come in 2 poles to make up a magnetic field. Okay, so how does that fit into our expansion here? Well, all that means is that when you integrate over dl prime by itself, then that's equal to 0. Integration over the closed loop, the closed path, gives you a 0. Okay, so that means that the dominant term is the dipole. So magnetic fields, their lowest order term is going to be a dipole. Okay, so let's write out the dipole term. Mu 0 I over 4 pi, the integral r primed, so this is the n equals 1 term, cosine alpha dl prime, and the one thing I missed was the r squared out front. Okay, so here is our term. So we can now we can integrate this. Now, what about this cosine alpha? What are we going to do about that? Because we want to write this in terms of dl. So what I'm going to do is, if we go back to our picture, cosine alpha is essentially the dot product of the r and the r prime. So therefore I can write out cosine alpha is r hat dotted into r primed. Okay, so let's plug that into the integral. Mu 0 I over 4 pi r squared, the integral of r prime cosine alpha is just, that's, okay, sorry. R prime cosine alpha is this dot product. So that's why there's a unit vector in r, because there's no r term in front of the cosine. There's only the r prime term. Okay, so that means we have now r dotted into r prime, and we're going to integrate over the primes. Now, I could do is I could rewrite this integral as an area, a surface area integral like so. And now I get rid of everything, and all I have to do is integrate over the area. And what is this area? The area is the area of the closed loop. So I'm always integrating over a closed loop, dl, dot, dot, dot in front of it. And so that means in here, I'm always forming a surface area right there. Okay, so then basically from there, what I have is a new equation, which I can rewrite as the dipole magnetic potential as a function of r is mu0 over 4 pi m cross product with r hat divided by r squared, which looks a lot like our electric dipole, where we had an electric dipole term dot product into the distance vector. And so that means m, by analogy, is the magnetic dipole moment, which we've defined now as the current times the area. Oops. The area vector. Or if it's a constant current or uniform current, then it's just the current times the area, including the direction of the area vector. So I'll redraw the picture. So what we have is our area right here. Our current is flowing in that direction, and we should have some area vector n hat. So what you could do is you could think of writing this area vector as the magnitude of the area A times that direction of the area, which is basically the normal to the plane that is the area, or the normal of the area if you have something like a sphere. It's just that normal, that radial vector pointing perpendicular to the surface of the sphere. Okay, so now we have something which is this new formula for the magnetic dipole moment, which is analogous to the formula that we have for the electric dipole moment, where there's a 1 over r squared dependence, and then there's a dipole moment that you have to include into the formula. So for the magnetic case, it's a vector. In the magnetic case, the potential is a vector, so we have to have the cross product between the magnetic moment and the direction. For the case of the electric potential is a scalar, so in that case we took the dot product of the dipole moment with the direction. So in the next lecture we'll do is go over an example using the magnetic dipole moment.